Hey there, industrial controller designers. Before we get started today, let's pop in our 8 tracks with some disco background music, maybe a little Donna Summer, perhaps. Push the buttons to check our digital watches with the 7 segment display. Of course, and put away those slide rules. We get to use fancy reverse Polish notation calculators these days. Do you ever feel like industrial controller design doesn't get any new innovation? I mean, all of these other types of engineers have these 64-bit supercomputers on a chip for 15 cents that do whatever they need in their designs, and we're still here using these big, expensive, clunky logic gates from 1979. When do we get something new and cool? Hi, I'm Amelia Dalton, host of Chalk Talk and Industrial Logic Controller Designers. This is our lucky day. My guest is Tom Wolf from Nexperia, and we're talking about a whole new load of new innovations in industrial control technology that will finally bring us back out of the 70s. Well, except those plaid double knit slacks. You're going to have to fix that situation yourselves. And before we get started, don't forget to click that link. There you can find more information about logic innovations for the industrial control space from Nexperia. Hi, Tom. Thank you so much for joining me.
Why, thank you, Amelia. I'm glad to be here.
Okay, so Tom, it seems like logic has been around forever, but what specific innovations are we talking about today?
Well, that's the real purpose of the presentation. Because logic has been around for so long, a lot of engineers don't understand that there's been new changes for it. Logic is doing a lot of the same functions as it did, but it's now doing them with new packages, new styles, new functions. And that's what we really want to talk about today.
That's great, but can we get into specifics with a real application?
What I'll start with is the agenda. We want to look at a case study. It's nice to talk just generically about you can save a lot of money with these parts. Let's look about a very specific example so you can see where it really applies. And then we'll get into them specifically. What are these new innovations that you may or may not have heard of? And then really the most important thing is we want to talk about what are the benefits, what are the savings once you apply these applications for. So that's really the goal of today. With that, I'd like to start with a very specific case study, and we're going to look at the industrial controller marketplace. Now, you might be thinking, I don't build industrial controllers. These are for robots and conveyor belts and things like that. But in reality, the industrial marketplace is the none of the above category. For example, health equipment, monitoring equipment, MRI machines, power tools, welding equipment, HVAC systems. They really do the same thing. They look at the environment, they sense it, they make changes and decisions based on that, and then they alter the environment around them. So we can start with an industrial controller, and here's a picture of it. It's courtesy of National Instruments, but many people build the same sort of thing. The thing to remember is that these boxes have a variety of sensors, a lot of inputs from different places for temperature, position, humidity, speed, things like that. They process them with somebody's CPU, somebody's general controller, and then they output information. They may turn on a furnace, they may run a conveyor belt, they may turn on the air conditioning in your house. They have some sort of interface, which might be graphical or audio on them. All of these applications will have the same problem. They're size constraint, they're cost constraint, they have to be high reliability. So they all have a common set of needs. A lot of inputs, a lot of outputs, need to last a long time, they're cost sensitive, and all those things are where these innovations really come in and have a big advantage.
Okay, cool. Can you give me some more details about this one?
Yeah, so let's look at some common logic that's found in industrial controller application marketplace, because there's a lot of them. If we look at the same part numbers, we see them over and over again. They are generically the logic functions, the AND gates, the OR gates, the buffers, all those devices which again have been around since the 1960s and 1970s. They're still used over and over again. Well, you can make them better than they were 50 years ago. Then there's the whole family of translation logic. Translation has to do with taking a microprocessor that runs at 1.2 volts and having it talk to peripheral devices that run at 5 volts. How do I connect these two different electrical languages together? There's a lot of new solutions for that as well too. Then there's the other category, things where we see the same application coming up over and over again. Why do it the old way when there's a new way of integrating it together? So we'll look specifically at those in terms of some analog switches and some clock dividers, and again, some very specific part numbers for some very specific applications.
Okay, so we don't need to talk about all logic devices since the beginning of time. Let's just talk about the new stuff.
Excellent. So let's look at the logic innovations which have occurred in the last, say, 5 years or so, because that's really where the growth has been. And here's a list of, looks like 8 or 9 parts that we want to talk about, some of them in detail, but some of them just as an overview to give you an idea of what has really changed in the logic market over the last several years.
First on the list was combination logic, I believe. So tell me more about that.
Combination logic is the whole idea of combining multiple parts into a single package. Now, in the beginning of logic time, you could buy parts which were called quad buffers, hex buffers, octal buffers, which meant you had 4 or 6 or 8 of the same gate type inside a package. Well, in today's applications, you don't tend to need 4, 6, or 8 of the same thing. You want 1 or 2 of them. So even today, most packages have 2 of the same things, 2 AND gates, 2 OR gates, 2 inverters inside. If that's not what you need, though, wouldn't it be better if we could make a part that has 2 different types of functions inside the same package? So that's the whole idea of combination logic. We combine 2 different parts inside the same package device, so you don't have to have 2 different packages. They're both combined already in the first place. So we have 2 different kinds. One of them is what we call a single gate, where the 2 different gates are connected together inside. The output of an AND gate feeds into an OR gate, or an OR into an AND, or whatever. So it's one path through the device. That's why we call it a one gate or a one channel device. We also have 2 channel devices where the 2 devices are not physically connected. The OR gate and the AND gate reside inside the same package, but they are not connected to each other, so you can use them independently. This gives you a lot of versatility when you're designing logic gates or logic functions, because instead of having to have 2 packages, connect them together, source the 2 different parts, you can put them together. So you get basically a 50% space savings. Instead of 2 6-pin packages, it's 1 6-pin package. You also end up saving power. Each part consumes about the same amount of power. When I combine them together, I have negligible additional power for that one part, so I'm saving roughly 50% of the power. Sometimes I get improved speeds. If I'm connecting these devices internally, I save some speed on that as well too. And overall, where the rubber hits the road, it's reduced assembly and material cost. You don't have to deal with 2 packages and chasing them around. It's just one part on the board now. So it's one package with 2 independent functions, or one package with 2 connected functions. You decide for your particular application.
Okay, next up, configurable.
Exactly. There's 2 different kinds of configurable logic, and they feed off of each other. The first one is this idea of single configurable logic. Now, stay with me for a second on this. A configurable logic gate is a single gate which can be configured to one of 7 different Boolean functions only by changing the signal connections. And you're going, okay, it's programmable. No, it's not a programmable device. Forget everything you knew about ASICs and EPLDs and parts like that. It is a device that it changes its personality based on how it is connected to the circuit board itself. So sometimes we call them PCB configurable devices because that's what makes them different, how you hook them up. So let's look at each one. This is the internal diagram of the 57 family, and there's some other families, don't worry about that. But it has 6 pins on it. 3 of them are fixed. Power and ground, they're stuck. Output pin, that's on a predefined pin. I've got 3 input pins, however. Depending on how I hook my signal to those 3 input pins, the part takes on a different personality. So for example, in the lower left here, let's configure this 57 function as an AND gate. If I connect VCC to pin A and my 2 input signals to A and B, it ANDs the function on the output side. Now with making no changes to the part at all, to the physical device, connect the wires up to different places, to different input pins on the device as shown on the lower right, and I get a NOR function out of it instead. So exact same piece of silicon, no change to the silicon, but it can be an AND gate when it's used on one part of the board, and the exact same part can behave like a NOR gate on the other side. It's the perfect part for impersonating. It's a chameleon. It takes on whatever function you need it to be where it works. Now here's a diagram of all the different functions. Don't worry about the details, but what this means is that by using a 97 function or a 57 or 98 or 58, you get a different group of functions inside. Some has ANDs, ORs, and NOTs. Some has buffers and exclusive ORs and inverters. You look at your list of total logic gates you need and you go, aha, the 58 gives me all the functions that I need in a single part. That's the solution for you. So this gives you the versatility for whatever your logic parts are. There's probably a configurable logic device that will fit in and give you the functionality that you need. The other cool function that you get on configurable logic devices is that all the inputs have Schmitt trigger inputs on them. Now remember, Schmitt trigger inputs are used for cleaning up noisy signals. In the industrial marketplace, you have a lot of noise coming from sensors and things like that. So these are really useful for cleaning up that signal. The problem with Schmitt triggers is that there's not a lot of prime gates. In other words, old-fashioned gates that have them on them. You may not be able to buy an or a NOR or an exclusive NOR that has Schmitt trigger inputs. Configurable Logic has it. So you get it for free, basically. You need an exclusive NOR with Schmitt input triggers? Here's the part. Use this and it replaces all those prime gates that are really hard to find nowadays anyway. Another neat feature about configurable logic is that there's something called compound gates inside. Now, this is another one of those free benefits that you get that at first glance you go, that doesn't do any good. And then once you really understand it, you go, this is a really useful function. Each configurable logic family has 7 different Boolean functions because you can hook up the input pins, basically 7 unique ways on them. 5 of these functions are the common logic gates you're used to. The AND, the OR, the exclusive OR, the stuff that's been around forever. But 2 of these 7 functions are kind of strange devices. They're a NAND gate with 1 inverted input. And I'll admit, when I first saw those, I go, who's going to use that function? Well, it turns out it's a really useful function on it. So we call them compound because they're not a basic AND gate. They are an AND gate with 1 inverted input on them. So for example, in the 57 family, one of them is a NAND with 1 inverted input. That could replace 2 prime gates, which are in Boolean part numbering schemes, the -00 function, a 74AUP1G00, and an 04. So 2 physical devices can be replaced by 1 single configurable logic package. That's what we mean by compound gates. So let's look in detail on the 57 function in particular. Now, down the left side are those 7 functions we keep talking about, inverters and NANDs and things like that. But look across the chart, particularly down on the far right side. The far right column says these are the part numbers of prime logic gates which would be required to implement that function. In other words, the top one, the inverter, it's a 1-for-1 replacement. But if you go all the way down the list, notice that the exclusive NOR function with Schmitt trigger input, it would take you 3 discrete physical devices to implement that function. However, a configurable logic device can do those 3 devices, can replace them with just 1 device. That's the benefit of a compound logic function in configurable logic. Now, compound functions give you a lot of benefits. The first one is in board savings. If I had 2 or 3, or there's somewhere there's more physical devices, I'm replacing those 3 physical devices. They all tend to be 6-pin packages, so I've gone from 2 6-pin packages to 1 6-pin package. Pretty easy math. It's a 50% reduction in the number of devices that I have, which means at least a 50% savings in the board space. That doesn't include routing space and standoff and all the other things. So you're going to save a considerable amount of space by using compound functions. But the next function is that I get power savings as well too. Each physical package device consumes so much power. It has input, output protection, and things like that, which consume power. AUP1G14, for example, is 0.5 microamp static. Well, the 1G132, that's another 0.5 microamps. However, a single AUP1G57 configured to be the NAND with the inverted input on it, the whole device only consumes 0.5 microamps. So I'm getting a 50% power savings as well too. That means it's a way for me to take 2 parts, reduce them, and save power at the same time. And finally, there's a speed improvement. When I connect parts internally, I don't need input and output buffers on them. So my 2 package devices would take 2.5 nanoseconds each, total of 5 nanoseconds for the signal to get through. However, because they're connected internally in a 1G57 configured as a compound, it only takes 2.9 nanoseconds for a signal to get through. So I've saved board space, I've saved power, and I've made the part faster by simplifying the design. That's the advantage of this compound function. It compounds the savings in more than one way as you're using this function.
All right, so Tom, what are the real benefits here?
And that's where it's important now. We can talk about these nice theoretical things, but the real point is that this saves real dollars. So we'll talk about actual dollar savings. If I can implement all of the features of configurable logic, I can reduce the number of different devices purchased. My original bill of materials might have had 1 AND gate, 1 OR gate, 1 inverter. Those are 3 different part numbers. I don't have to buy 3 different part numbers anymore. I can buy just 1 part number instead. This also means that I have a fewer total number of devices purchased. If I'm using the compound function, instead of buying 6 different parts that are implementing 2 different functions, I've reduced that to 2 different parts. So the total number of silicon devices on my board has been reduced if I can implement compound functions. And then finally, and this is where the savings really comes in, I'm buying a higher quantity of fewer types of part numbers. So instead of buying 1 each of 7 different part numbers, I'm buying 7 of 1 part numbers. And everybody knows as you move the price column over to the right, the price goes down. So it's a real physical way of saving money with these logic functions. Same function, better performance, but savings in a variety of different ways.
Okay, so we talked about single configurable, but what about dual?
If you got all these nice savings from single, guess what? There's another part which is a dual configurable device. It gives you twice of everything. And it simply is two configurable logic devices built into a single package. They're independent. So I have a 57 function and another 57 function inside. Inside the same package, I can make that same silicon mask act as one OR gate and one AND gate, or two AND gates, or two exclusive ORs, or you mix and match them the way you want. In other words, a dual configurable logic device is a self-configurable combination logic device that we already talked about. You build it the way that you want inside. And all the savings in terms of power, in terms of performance, in terms of space savings, just double all those numbers again too. We're even looking at the possibility of building what we call a asymmetrical dual configurable device. Instead of having two 57 functions inside, would it make sense to build one that has a 57 and a 58 inside so you can get exclusive ORs and buffers here and inverters and something else on the other side? If it makes sense, that's the kind of thing we want to build.
Okay, so we've talked about silicon. Now, how do you package these parts?
So these are the silicon innovations. These are what you can do from a functionality point of view. But you still have to put this silicon into a package. Now, packages have really evolved over time. Everybody remembers the old battleship dip packages. Remember, they were like a couple inches long and all these pins down the side of them, and the pins would bend and everything. Good news is dip packages are pretty much obsolete. Nobody uses them anymore. But there's been a trend from moving from the through-hole technology to the pin devices, which we call the Pico gate devices. They have the little gull wings that come out on each side. And then moving from the Pico gate to leadless packages. We call them the MicroPak. They have no leads sticking out on them, so I don't have to worry about bent pins and things like that. In general, the technology, though, is that as packages got smaller and smaller, the lead pitch, the distance between the leads, also got smaller at the same time. What it boils down to is that we can probably make a package that is so small that nobody can physically handle it. The pins would be so close as that they're essentially on top of each other. So smaller is not always better. There has to be a better solution than that.
Right? Smaller is better, but at some point it gets so small that you can't actually manufacture it.
And that's the trouble with the smaller pad pitch. Now remember, pitch is the distance between the pins, actually the center to center of each one. So as parts get smaller and smaller, we move from 0.1 inches down to 0.5 millimeters to 0.4 to 0.3 to 0.22 millimeters. These parts are extremely small between the two. So here's a photo of it to actually represent what the PCB looks like from the top, the distance between the pads. And I want to put an edge view here because that's going to be really important in the next picture. Now remember how parts are manufactured. We use something called a solder mask that puts the solder on the PCB in the places where the part is going to be put. So this is what it looks like from the side view and some of the terminology for it. You have the stencil frame, which is a piece of metal, not much thicker than a piece of aluminum foil, actually about 100 microns thick. It has holes punched through it called apertures. What I do then is I take my solder paste, I squeegee it across the board so that the solder squirts down through the little apertures onto the PCB down below. So that measures the exact amount of solder which goes onto each one of the pads. Now, as the board gets smaller and smaller and the pitch gets smaller, the apertures get closer and closer to each other. At some point, I get so much solder through that aperture is that it just globs up all over the board and I get shorts and it's a mess. So when you start getting below about 0.4 millimeters, that's about where most manufacturing engineers claim, below 0.4 millimeter pitch, you have to start doing something special, which is what's called a step-down solder mask. A step-down solder mask is just that. The mask steps down. So instead of being 100 microns thick, it's 80 microns. You're talking very thin aluminum foil between the two. And I have to use a special type of solder, which is more expensive and more difficult to use. So yes, you can indeed mount a part which has less than 0.4 millimeter pitch. A lot of people in the mobile phone market do it all the time, but it has additional cost, it has limitations on it. It is a more expensive and more difficult process to do. In the average world, you don't want to do that. So is there a way to build a part which is small, but has reasonable lead pitch so I don't have to go through this special manufacturing process? That's the whole idea of these devices in the first place. So what's the problem with the step-down solder mask? Like we said, it's expensive to make, it requires a Type 4 solder paste, they're fragile, they need replacement more frequently, and in general, it restricts the placement of the components. So is there a solution for this manufacturing? Is there a way of making a part that doesn't require these masks? That's the whole goal, of course.
So, what is Nexperia doing to solve this problem?
Our solution to avoiding step-down mask is we designed a part called the X2 SON package. It's affectionately known as the diamond package sometime because look at the part, it's got a diamond right in the middle of it. The whole concept behind this is how small of a package can you make with the maximum size lead pitch. Now, since the beginning of logic time, everybody put the leads in nice, neat rows down both sides of the package. We looked at it and said, can't we go diagonally across the part because there's more distance on it? So what you end up, as the photo shows here, is a part, 5 pads on it, 0.8 millimeters on a side, but it's more than 0.4 millimeter pitch between those pads. That means this device, and here it is sitting on the head of a pin, can be manufactured using normal manufacturing process, normal solder sensors, normal solder, all the things that are used on the rest of the line can be used for this very, very tiny part as well too. That's the innovation. Make it as small as you can, but make it still easy and affordable to manufacture this device.
So, Tom, would this work for any of the common logic functions?
What's neat about this is that it's not just a single part. The Exxon 2 package is available in 4 pins, 5 pins, 6 pins, and 8 pins. Why are those numbers significant? Well, all of the single gate logic devices that we talked about at the beginning of the presentation, that covers all of those parts. So essentially any logic function, including most of the combination devices, most of the configurable logic devices, can be put into this new package. So the newest silicon innovation fits into the newest packaging innovation.
Okay, so moving away from packaging, let's go down the list to innovations in translation.
Let's talk about translation for a while. Translation becomes more and more critical in the industrial controller marketplace because of the length of time that these parts are made. For example, they were first designed with 5-volt microcontrollers, and all the peripheral devices were 5 volts, easy to connect them together. Well, microprocessors got fancier and they started running at 3.3 volts and then 2.2 volts and 1.2 and 1 volt, and the voltage kept going lower and lower. Well, guess what? All the peripheral devices, the motor controllers and the servos and the HVAC solenoids and all this stuff you were controlling, it stayed at 5 volts or 3.3. So you have this mismatch between the two. It's like two people speaking two different languages. The parts couldn't talk to each other anymore. So there's been this huge need for translation devices, the ability for one device to talk to another even though they operate at different voltages. So that's the concept of it. So we need parts which can cover all the markets from 5 volts to 15 volts at the high voltage range, from 3.3 down. And how can I connect all these two together? Well, we have a lot of innovations in those as well.
Okay, so tell me about your solutions.
Let's start with the first one, the 74 LVT 1T family. Now, this is a whole family of devices. It is a logic device, an OR gate, that has a translator built into the front of it. So you can get your ands, your ORs, exclusive ORs, all the normal parts, but it can translate anything inside. So this part will operate anywhere from 1.6 to 5.5 volts, but it can understand lower voltage or higher voltage families. So run it at whatever voltage you want. It will translate up the signals for parts which run at a lower voltage, and it can translate down signals that run from a higher voltage family. So it's kind of a universal device. Anything from that 1.6 to 5.5 volt range, here's a single part that can cover all of them.
Now, Tom, what if I want a narrow range?
The 74 AUP1T family gives you the ability to narrow down the voltage range. As you narrow down the voltage range, the power consumption goes down. So for those really power critical applications, the cellular phones, the smart watches, the little battery powered devices, this is a way of really optimizing the power on it. If you don't need the wide range of translations, then pick the AUP family because that gives you a range from 2.3 to 3.6. That's the lithium battery voltage where most rechargeable devices are, and it gives you translations of the voltages higher and lower than that specific voltage.
Now, I am really sick of having my translator as a separate part. Can we do anything about that?
Let's look at that idea of combination logic we did before, which was just a couple different gates put together. You can make that more sophisticated. For example, in the industrial marketplace, one of the most common devices is the 595 function because it's a serial in, parallel out shift register. They're used for driving all the LEDs on control panels and car dashboards and idiot lights and things like that. It's a very nice way of driving them. So everybody uses 595 functions. Well, 595 driving LEDs wants to run at 5 volts or sometimes more. But your microcontroller runs at a lower volt. So what we kept seeing is this application where it was a voltage translator and a 595, two individual device packages. Why don't we combine them together? So we introduced this part, the 74 LVC 8T595, which is a translator and a 595 shift register into a single package. So what we did for gates in combinational logic, we do here with a voltage translator and a 595 shift register. Same concept, just a little more complex.
Now, Tom, I usually end up with a bunch of extra pins I don't need. Why are some packages so big?
One of the most common packages used in logic applications, in industrial applications in particular, is a clock divider. I have a 1 megahertz clock coming in. I want to divide it by 16, by 64, by 128, all these different subdivisions of the original clock. So what you would typically buy would be a part like a 4020, which you'd bring one pin in, and it has a divide by 6, divide by 8, divide by 4, divide by 32. You pick the one that you want, you hook it up. And the problem was you never use the other pins. You're paying for pins that never got hooked up on the board in the first place. We looked at that and we said, people are buying a 14-pin package, but they only need 5 of those pins. Let's take the exact same piece of silicon, put it inside a 5-pin package, and you don't have to pay for those packages anymore. So this family has 5-pin variants, and you pick the one that you want. I want the one that just divides by 16, just divide by 64, just by a million, whatever the variation happens to be on it. So it's this idea of let's take the same piece of silicon, keep its functionality, but put it into a much smaller, more cost-effective package.
Now, what if I want to run at a low voltage and switch high voltage signals?
The CBT family stands for crossbar technology, and it's the idea of switching high-speed signals with a logic function. If I have different memory banks on my computer or my controller, for example. In the past, there were high-voltage, high-switching signal devices. Those were called the CBTs. You operated the part at 5 volts, and it could switch 5-volt signals. All well and good when everybody ran at 5 volts. Then everybody switched to low voltage, and we came up with the CBT LV family. Ran at 3.3 volts, could switch 3.3-volt signals. Very nice for low voltage. Well, that wasn't good enough. Now we start seeing applications where you want to run the device at 3.3 volts, but you have to switch 5-volt signals. I need a translator function put together in one. So we developed the CB3Q family. It runs at low voltage, but it can switch high voltage signals through it. So you get all the combinations that you need out of it. Low voltage, high voltage, or low and high voltage. All the same functionality, but just pick the part which fits your translation and signal needs.
All of these new low voltage innovations are great, but why can't we use them on older 5-volt parts?
And that's really it. A lot of new technology has been applied to the low voltage parts, but there's still people using 5 volts, particularly in the industrial marketplace, because you built a brand new CPU for it, but you're still using peripherals that have been installed on conveyor belts since the 1980s. So how can I get the new efficiencies and performance of a low voltage family on a high voltage part? That's what the LVA logic family is. So it's your same parts, OR gates, AND gates, functions like that, but it has a feature called I-off on it. Now, if you use low voltage, you're familiar with I-off already. It means when I turn off the power to the pin, it disconnects the inputs and the outputs so voltage can't flow accidentally backwards through it or forwards through it. That used to be only available in low voltage families. Now it's available in 5 voltage families as well too.
All right, let's get down to some brass tacks here. Will this save me money, Tom?
And that's the real point of this presentation. These are all really neat technologies. And from a technologist point of view, I go, really good, really creative, but do they really save money? And that's where you really want to get your arms around these things. So let's look at it from 2 points of view. First, there is the direct cost benefits for these devices. If I can take 2 devices that I used to have before and convert them to 1 device, that's clearly a way of saving money on it. For example, a combination logic device may reduce my package count by as much as 3 times. If I have the right combinations on my board, I may be able to get rid of 3 physical packages and replace them with 1 package. Easy to do the math on that. If each part costs a nickel, for example, I just save 10 cents out of my 15-cent solution just by implementing these compound functions. A single configurable device may reduce my package count by 2 to 1, 3 to 1. There's some examples where it's more than that as well too. So again, I'm reducing the physical number of devices on my board. It's pretty easy to do the savings. I don't have to buy another part anymore. Dual configurable parts, if you can use those, you're saving even more, sometimes as much as 6 to 1. We've seen one model where it's a 10 to 1 savings. 10 physical devices were replaced by 1 physical device. That adds up really quick. Now, I also get package cost reductions because parts in the package roughly cost the same amount. A 6-pin package holding 2 gates or a 6-pin package holding 1 gate, they're roughly the same price. So in that case, by combining some of these parts together, I'm getting a direct savings by just getting rid of the number of packages that I had. The most important thing to remember, though, is that newer packages tend to have the potential for better cost savings. We mentioned the DIP package before. Nobody makes it. The price is only going up because manufacturers are out of it. Well, all packages follow that same timeline. Originally, they're new. They cost a little bit more. They hit a maturity part where everybody's making them. They're the cheapest they'll ever be. Then manufacturers start saying, I don't want to make this anymore. People leave the market and the price goes up again. So there's constant shift of packages. Moving to a newer package at first may seem more expensive, but what it means is that when that part matures, it will be the cheapest. Let's face it, a 64-pin Battleship dip had a lot of material inside it. A little 6-pin Exxon 2 package, it has essentially no material in it by comparison. It will cost much less once it hits the maturity point on it. So moving to new packages gives you that scale as well too. And then finally, this is a solution where you're going to save money that has nothing to do with our semiconductor device. Because you don't need as much board space, you can reduce the size of the PCB itself. You may think, industrial controller, I got tons of space. Yeah, industrial controllers mean thermostats, they need watches, they mean power tools where everything is space constrained. So reducing the size of that PCB is a real cost. It's so many pennies per square millimeter for that board, I make that saving on it. It also means that if my PCB is smaller, my entire product can be smaller. I can make a smaller tool, a smaller thermostat, a smaller controller, which means I multiply that savings even more. The entire product price may go down because I've reduced the number of components by using some of these innovations.
All right. And what else are we saving?
The other thing too is what I like to call intangible savings. These are things which you will agree will save you money, but I can't put a dollar amount on them. For example, manufacturing savings. The board designer will often look at a part and say, hey, this part is cheaper, let me use it here, without thinking of what the cost feed through to the manufacturing line is. In this case, there's a lot of manufacturing saving. For example, when I combine 2 or more functions into one package, I reduce the pick and place time on my assembly line. I don't have to load 2 parts on the board, I only have to do 1. So I get a direct time savings and a direct cost savings when I manufacture these boards itself. Now, configurable logic also replaces the number of unique reels. Remember, on a pick and place machine, I may have 8 or 16 or 32 reels which hold my 8 or 16 or 32 different devices. If I have one device which replaces 7, I just got rid of 6 of my reels, which means my pick and place equipment becomes simpler. It also means that if the machine gets filled up, I don't have to run the board through it twice with a different set of reels. I may only have to run through the pick and place machine once. So there is real dollar savings in the amount of time and the amount of manufacturing cost, which has nothing to do with the price of the device itself. It's the cost of it. The next one too is the qualification savings. Now this is a real tough one. Qualification cost for a new part costs anywhere from $0, the engineer goes, looks good to me, let's use it, up to, we've heard automotive qualifications may cost as much as $100,000 each. It's a significant amount of money. If I can reduce the number of parts on my board, I reduce the number of qualifications and I save directly on that number. The next thing is in power savings. If I can reduce the amount of power that these parts use, I may be able to reduce the size of my power supply. Maybe, maybe not. The real thing though in battery applications today is if I can reduce the power, I can either reduce the size of my battery, which makes my product smaller and cost less, or I can keep the battery I had and I get longer battery life out of it. In either case, it's a benefit. I'm not taxing the battery as much, which gives me a lot more efficiency by saving power on it. The next intangible is the reliability savings. If I can get rid of a lot of pins by going from 3 6-pins to 1 6-pin package, I just got rid of 12 pins. Every pin is a failure point because of solder, reliability, corrosion, whatever. Every time I can get rid of a point of failure, there is some cost savings in reliability. My product will last longer. It's intangible, but there is indeed a value in reliability. Also, in the other side of it is the manufacturer reworking. It is a lot easier to work on a part that has a large lead pitch, a smaller number of devices with bigger lead pitch, than working on a lot of devices that have smaller lead pitch on them. So the rework, the ability for somebody to fix a board or to fix it either out of manufacturing or to a customer repair is much easier with the new packaging technologies, simply because they're easier to solder and easier to rework. And finally, there's an inventory savings. Instead of having to stock 7 different parts, I only have to stock 1. That means my order, my inventory, the parts I have on stand, all of that is reduced. So like I said, I call these intangible. I think everybody will agree that there's savings from manufacturing, reliability, from inventory, from qualifications. I can't put a number on them, but these can be very significant savings. Again, which have nothing to do with saving a penny on the part. You may save 100 times that amount in your manufacturing. So what I like to summarize with is that we've talked about a specific market, the industrial application marketplace. These logic innovations can be applied across virtually any electronics industry. So I'd like to challenge you. What is your case study? What can logic innovations do for you?
Excellent. This was super cool. Now I'm going to click that link and go to the Mauser site to find more information about your solutions. And I think that's all I have time for today. Thank you so much for joining me, Tom.
Thank you so much for your time, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about logic innovations for the industrial control space from Nexperia. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal Can't miss it right across the top. Or head on over to YouTube. Keyword EE Journal.